Hey, welcome back to ClearSpot. Building an agentic orchestration system isn't like buying an off-the-shelf monitoring tool. You're not installing another dashboard. You're designing an intelligent infrastructure layer, one that sits on top of your SCADA system, your inverters, your sensors, and adds autonomous decision-making without disrupting the systems you trust. And here's the key. It must integrate seamlessly. It cannot break your existing operations. It cannot force you to replace infrastructure. In this video, we're going to break down what modern agentic orchestration architecture really is. The layers, the data flows, the autonomous agents, how systems communicate, how decisions are made, validated, and executed, and most importantly, how this architecture scales from one site to 50 sites, managing hundreds of thousands of data points per minute, while remaining safe and operator-controlled. Let's dive in. Modern agentic orchestration is built on 4 layers. These layers are decoupled by design. They scale independently, and together, they create a closed-loop intelligent system. Layer 1, the foundation layer, is everything you already own. SCADA systems, SMA, Enphase, Proteus, Growatt, Solis inverters, DC combiner boxes, weather stations, sensors like irradiance, module temperature, wind speed, humidity, trackers, and batteries. This layer does not change. Agentic orchestration doesn't replace. It leverages. Layer 2, the integration layer, is the universal translator. Inverters speak different languages. SunSpec Modbus Enphase Enlighten API, Fronius Solar API. Your SCADA might expose MQTT. Your ERP uses SQL. Your weather station uses HTTP. The integration layer normalizes all of these into one standardized schema. It adds timestamps, cleans data, flags anomalies, and delivers real-time streams upwards into the system. Layer 3, the decision layer, is where autonomy lives. Multiple specialized agents run in parallel. Performance agent, maintenance agent, safety agent, compliance agent, optimization agent. Each agent sees its own filtered view of the data and makes domain-specific decisions. Then they coordinate through a message bus. These decisions happen in milliseconds. Layer 4, the execution layer, is where the decision layer decides and the execution layer acts. Update inverter set points, shift tracker angles, send alerts, trigger maintenance workflows, modify battery schedules. All commands pass through validations before reaching hardware. This entire system forms a closed autonomous loop, data to decision to action to feedback to learning. And this loop runs continuously. If the 4-layer architecture is the skeleton, the data pipeline is the circulatory system. Data collection. Solar assets produce massive diverse streams like 5 to 15 seconds inverter telemetry, 10 to 30 seconds sensor data, 1 to 5 seconds SCADA data, 15-minute satellite weather, daily market pricing, and quarterly maintenance data. Structured, unstructured, real-time, historical, the system must ingest all of it. Data ingestion. Each data type uses a different protocol, such as MQTT, REST, Modbus, SQL, FTP, and vendor APIs. Adapters convert everything into a standard internal schema. They validate. Are values in range? Is formatting correct? Are timestamps synced? Anomalous data is quarantined automatically. Data enrichment. Raw data is rarely useful alone. Enrichment adds context, like irradiance context, historical baselines, maintenance records, weather anomalies, grid events, and market signals. One data point becomes a multi-dimensional feature. Storage architecture. The system uses multiple databases, such as time series DB for real-time signals, data warehouse for long-term analytics, feature store for machine learning inputs, and object storage for images, PDFs, sensor dumps. No single database is overloaded. Each is optimized for its role. Access control. Not all agents see all data. Performance agent shouldn't see pricing. Optimization. Agent shouldn't see raw thermographic imagery. Role-based access enhances safety and compliance. Scalability pattern. To scale portfolio-wide, real-time processing stays local. Batch processing moves to cloud. Heavy analysis runs asynchronously, and sites operate autonomously if disconnected. This avoids bottlenecks and creates a resilient distributed system. Here's where true agentic orchestration really shines. We've got multiple agents cooperating in real time. They communicate over a message bus, publishing signals. For example, the performance agent might say, "New operating point recommended, 96%. Meanwhile, the maintenance agent could report, "Component wear detected, derate advised." And the safety agent might add, "Thermal stress risk increasing." Agents subscribe to messages that are relevant to them, so they're always in the loop. Now, conflicts are totally normal. Performance may want 100% output, but safety might cap it at 92%. That's where the arbitrator steps in and evaluates domain importance, safety overrides, model confidence, revenue impacts, and degradation impacts. In the end, the system might decide on 97% with thermal guardrails. The system is continuously learning from outcomes. If, let's say, cooling performed better than predicted, the model adjusts. If degradation accelerated unexpectedly, the maintenance model gets updated. And if the weather prediction was off, the system modifies its weights. Each agent becomes more accurate over time. Hierarchical decision-making happens on 3 layers. There's real-time, which is milliseconds, handling grid frequency, voltage excursions, inverter protection. Then tactical, which is seconds to minutes, like maintenance scheduling or cleaning triggers. And finally, strategic, which spans hours to days, covering budget allocation and portfolio optimization. Each layer informs the next without blocking. Real-time agents respond instantly, while strategic agents look at trends. Now, let's talk about real-world deployment. There's on-premise, cloud, and hybrid approaches. On-premise gives you the best latency and the highest control, but it's harder to scale. Cloud is the easiest to scale and offers automatic updates, but you need to trust the provider and have stable connectivity. Hybrid combines real-time at the site with batch processing in the cloud. So, really, the best of both worlds, though it does add complexity. Data residency and security are big concerns. Operators may require local-only processing, GDPR compliance, region-specific storage, or even zero-trust architectures. An advanced system supports all these variations. When it comes to integration depth, you've got choices. Shallow mode is advisory only. Medium mode lets you write to SCADA and monitor. Deep mode means full command execution. Operators get to choose the depth. Nothing is forced. There's a validation pipeline before any action happens. The agent validates, other agents cross-check. There's a system-wide safety validation and a hardware acceptance validation. Only after all that does the command execute. Observability and auditability are built in. Operators can ask, "Why was output derated?" Or, "What data triggered the decision?" They can check the confidence score and see the financial impact. Every decision is explainable. Nothing is a black box. And for scalability, adding 50 sites shouldn't multiply your compute costs by 50. Distributed real-time plus centralized strategic analysis enables sublinear scaling. Once the architecture is in place, new capabilities really start to emerge. At the portfolio level, across, say, 10 to 20 sites, you can move crews proactively, coordinate battery dispatch, predict region-wide failures, and maximize revenue across all assets. With predictive maintenance at scale, the system uses cross-site learning to predict failures 2 to 6 weeks out, optimize replacement timing, reduce unnecessary truck rolls, and extend equipment life. Dynamic pricing response is another big one. Markets move, and your system adapts. It charges batteries when prices fall, maximizes export when prices spike, and balances performance versus lifetime. For grid services, advanced systems can handle frequency response, reactive power control, voltage stability, and curtailment optimization. These are new revenue streams, and agents handle them autonomously. When you're evaluating agentic orchestration systems, look for a clear architectural explanation, layered separation of concerns, and proven integrations with your hardware. Make sure there's multi-layer validation for safety, a scalable distributed design machine learning that actually learns complete audit trails and transparent limitations and assumptions. Advanced vendors will show you how everything works. Basic vendors, well, they tend to hide behind buzzwords. Like, share, and subscribe for more solar insights. ClearSpot, smart device, smarter decisions.